Hi everyone, my name is Amin, for those of you who don't know me. So today I'm going to present a project that I've been working on for a couple of years. The whole sort of slides today, hopefully going to summarize the work that's been happened and give you a sort of flavor of the development throughout the project timeline and finish it up with some results that we recently got. So there we go. So that's the agenda for the talk. I'll start with some overview of what it is we're trying to solve, the objectives that we set ourselves at the beginning of the project, go through some of the radar development. I promise I won't bore you with details, but if you're interested, there's some hardware details there. And then finishing off with some results that we got from the first trial that took place. So if you attended the part one presentation, Una gave an introduction to what it is that we're trying to do. So bear with me if I sort of repeat those. That one. Yeah, so most people know volcanic eruptions as lava flowing from the top to the bottom, but mass flows from eruptions also consist of pyroclastic densities and laharas. Pyroclastic densities are quite interesting. They not only they travel really fast, but they consist of a mixture of things that they pick up along the way, and then they carry that throughout the flow on the mountain side of the volcano. These things sort of they erupt from the volcano, and then once they get to the crater, their behavior is quite stochastic. So we kind of understand how it erupts, but we don't know the behavior of it. And I'm not going to pretend I know everything about pyroclastic density, but the picture on the left is quite interesting because it shows how complicated the composition of a PDC is. So it's got rocks in it, it's got hot gases that take different paths from the flow. The top and the tail of the flow have different behavior. So and these kind of account for this sort of pyroclastic densities. They account for bulk of facilities and infrastructure damage, especially to farmers and people who live near the volcano. So to map these flows and especially to map them as soon as they take place, will help us understand the impact of them and hopefully help us to forecast their behavior in future flows. These sort of studies obviously require teams with multiple skills. So in this project, we've got engineers, we've got physicists, we've got geologists. And believe it or not, nothing will happen without local authorities. So it's always good to have those on board. So the objective that we set ourselves at the beginning of the project were build a custom-built radar that can first detect the volcano at several kilometers. B, pick up moving targets such as PDCs, and if we pick up a dozen of PDCs, then that will be a good success. But the data you get from the radar also sort of feeds into other objectives that other project members were looking at. So mostly modeling techniques and mapping the radar data with the data you get from optical images, so mainly drones. And there's also, so within the hardware requirements as well as the radar system, the objective was to also build a robust seismic sensor that will work in tandem with the radar. This is the geometry of the radar. So our target is a big active volcano. So obviously you want to be a few kilometers away. And because of the difference in terrain, the radar required to look up to the target rather than down. This is actually good because most of the antennas, well, I'll explain what frequency band the radar is at, but the antenna that were chosen, they had a natural sort of offset beam, which is quite helpful in this scenario. So the 3 or 4 general requirements for the system, where there's no power grid, so the system has to be powered by solar. Because of the power requirements, we can't have the system on all the time. So some sort of automatic detection and logging had to be taken in place. For this, a seismic sensor is deployed, so the radar is seismically triggered. And because it's a rough terrain, the radar has to withstand weather and other sort of conditions. So a portable regularized system would be quite beneficial. So on the bottom corner, you'll see the radar system. This the antennas will focus a beam and map a small spot on the mountain side of the volcano with a small degree of the beam width. So say 1.85 degrees for the antennas. At several kilometers, this will map a footprint of about sort of 200 meters on the volcano. And on the bottom here, this is a Google sort of Google Earth picture of as you would see, as the radar would see the volcano on the spore site. Yeah, so that's the geometry of the system. So I'll jump into the radar hardware. So our radar is based on frequency band within XKU band, with a band of 1 gigahertz. The architecture of the radar is FMCW radar, so most people in this room are quite familiar with that. The linear chirp that it produces has a period of about 10 milliseconds. So it's a trade-off. Sort of what's the speed of target you're looking at, where you want IF to fall in the frequency where it's falling, and yeah, so it's a trade-off between that. So we chose a 2 millisecond chirp, triangular obviously to get the velocity data. The transmit power really comes from a back envelope sort of a link budget famous radar equation, which you can see on the bottom left corner. So for point target, you can do quick modeling, and at about sort of say 3 or 6 kilometers, you should sort of aim for 20 dB or so SNR. So this then will feed into what sort of power you require to design radar. Our radar is designed with a 2 watts RF power. And the DC consumption of each bit is also listed on there. I'll go through them one by one if people are interested. So just going through the design itself, the radar, transmit radar, obviously starts with a source of a linear chirp, which is produced by synthesizers, so DDS. We produce a chirp from 400 to 1400 megahertz. We're using the fundamental signal of the DDS, and then that gets converted into an IF signal that gets conditioned. Then we're using a superhet architecture to directly up-convert that. And in fact, we high side inject that LO. And the RF again gets sort of conditioned, pre-amplified, and transmitted through a 2 watts amplifier. A replica chip or a replica or copy of that signal is then tapped off and shared with the receive signal to produce the intermediate frequency, as you would do with the FMCW radars. One difference for this system compared to others is that the transmit and the receive units are separated. Now, because we weren't restricted by size, we thought that because this is generally, there's a lot of high power spinning around. 2 watts is high frequency. The antennas are high gain. If there's any mismatch or poor isolation, all these signals will create problems, especially spurious levels and leakage and whatnot. So one way would be to isolate the receiver, keep it nice and tidy, and shield it from any incoming external sources. So you can see the connection between the receiver and the transmit is a shared LO signal. And on the receive side, the reverse happens. So the receive signal is mixed with a copy of the transmit signal, and IF frequency is produced. So once you go through the design of the board, obviously you have to make sure the layout and everything is custom built. This has got high frequency, so a careful piece of design has to be taken place. Once you do that and make sure the power supplies and everything all low noise, then it comes to the fun bit where you test the main RF signals at each chain, each test point of the signal, and make sure that they're doing what they're expected to do, and there's no nasty surprises. So the first thing you do, once you implement your DDS, you generate a chirp with your required parameters, and you can either sample that directly with a high sampling frequency oscilloscope and look at the signal. So you're looking for a nice high integrity sine wave, and you can see that they chirp periodicity from the envelope of that signal. Or you can get that signal through the IF and beat it with itself. By that, I mean you put that signal into a loop delay, ideally cable, and you mix it with itself, and then the same thing will happen. A nice little sound wave should come out, and the period of the chirp should also tally with what you programmed DDS with. And here on the bottom left corner again, you can see that signal. And the good thing about DDS is that it has this functionality where it sends a signal called drover that indicates that I'll finish my chirp now. I'm on to the next one. So I'll explain why that's useful. But it helps with speeding up the processing when you look up for chirps for especially FFT processing. And then so you look at obvious points in the radar. So you've got a spectrum of the IF, you spectrum of RF, and a spectrum of LO to see that they're nice and flat and no surprises are there. The other important bit on transmit is obviously the PA module. Given PA modules, especially those sort of powers, are quite costly, I decided to build my own. So based the module on a chip that you can buy, and you can sort of put it all together. They're sensitive to grounding, and they chuck out a lot of heat, so you have to design a careful sort of chassis to get the heat away. But once you do that, once you carefully put everything together, you can get a nice sort of 2 watts power out of these PAs. They're quite fussy about power them up, so these are quite sort of they're based on the PHEM technology. Means they require a negative voltage, negative and positive voltages in a special sequence. So they want to see the negative voltage first, and then the positive to pinch it off. And if you don't do that, you run a risk of damaging the PA. So here I'm showing the little biasing circuit that will create that sort of delay. So negative comes in first, and positive with delay. And the top shows you can actually push these power points a bit higher into their saturated power. So I'm actually driving them to get about 34 dBms. So that would give me about 1 dBm to get the signal from the PA to the antenna. So hopefully I'll end up about 2 watts at the antenna. And then once you've got all that bits, then you put it together. So obviously a transmitter unit have other bits in it. So there are power supplies, there are microcontrollers, obviously the casing and LEDs to indicate obvious sort of power on, off. So all of that are sort of shown here. So on the left is the finished product. So it's already sort of nice packaged up in the box and tested again for its integrity to make sure there's no isolation or anything. Receive again, so it's a bit simpler than transmit, but there's various ways of testing the receive. Obviously, if you've got a VNA with a frequency offset feature, that will make it easy for you, because then you can translate the frequencies and measure the receive in one go. If we don't have that, then there are a couple of other ways of doing that. One is to use a signal generator, split it off, so you create an LO, and then the other one RF, but then you can mix a low frequency where your IF should be, another signal generator, with the RF. So then when the IF and when an LO and RF are mixed, that IF will come out, and this way will help you to characterize your baseband characteristic of your receiver. So in our case, our baseband is designed for particular frequencies. Obviously, this frequency will correspond to a range that we're interested at. So we customize the filtering and amplification to happen at those frequencies that we're interested at. So to characterize that, there's this way. The other way to have a quick look at what this signal, single tone signal, looks like. So you look at sort of the SNR and phase noise. Is you have two separate signal generators that you feed the receiver and the IF comes out. With this, you can't really look at the flatness and the spectrum of the IF, because, as you know, the two signal generators will have different phases, and one frequency they might construct it at, or at the other frequency they might deconstruct it at. So you will get a ripple. You could tie them to a same reference terminal reference, but you still get phase differences. The other things to look at, again, the flatness of the obviously the RF and LO at the point where they're mixed, so to make sure that everything is nice and flat. Other things to look at is phase noise, SNR, and they are all in good sort of merits. So again, backboard was just the receive. The receive unit consists of other bits and bobs in it. So on the left, it shows where the receive board sits. On the right, there are other bits such as the digitizer, the seismic sensor, and all the power supplies. So once the radar board is placed in its final destination, which is the box, again, all the functionality were all tested just to make sure there's no isolation or anything else. We ended up with having a quite high gain receiver, which is really useful for us if we're looking at targets so if we want kilometers away. Still preserving a good SNR. The digitizer unit and the seismic unit also placed in the receive unit. So we are using a 20 megasecond digitizer by a company called Spectrum Instruments. It's a PCI Express interface, so it speeds up the data transfer, which is really good, and it's really high sampling frequency. We've got about 4 terabytes of storage capacity on board, and we at the time reckon with the data that we get, it should last us about a few months. It's about 6 or 7 months, which was plenty data to go around. I mentioned the radar it gets triggered by a seismic sensor. The seismic sensor is on the right. If you would you like to know more about that, then attend the part 1 presentation of this project. That was the work that was done by Una. He managed to make a really nice, robust seismic sensor that feeds the trigger signal to the radar, and it turns the radar on and off depending on what the parameters are set. The digitization and the automatic data logging is done on Windows and LabVIEW software. Credit to my colleagues Windows who helped realize this on LabVIEW. The flow chart is on the bottom of the slide. In a scenario when a seismic sensor has detected a signal, the PC and the radar boots up. Then this PC looks for a trigger signal from the seismic sensor. This is called T2 and T3. This is because if the PC wakes up and there is no activity, it sort of thinks, okay, this is the false alarm, I'll go back to sleep. So we're having a redundancy of the trigger signals. So it looks for that trigger signal, then the acquisition software comes on, records for a predefined length. So for our case, about 6 minutes. And then once this is elapsed, the software and the radar all is turned off, and then waits for the next trigger signal. And from booting up to acquiring raw data, it's about 17 seconds. So it's not the fastest, but that's okay because we're looking at a spot in the middle of the mountain volcano. So by the time the PDC erupted volcano, where the radar is looking at, that time is sufficient to start the recording. So then to power all of this, obviously you need a power supply unit. We ended up putting together 300 watts panels. And this is more than what the radar is sort of wants, but it's always good to have a bit of margin. And the power supply has the main battery in the main for the power supply box, but then also we had another bank of batteries that all daisy chained together to provide a bit of more juice. And yeah, so this power supply provides DC, 12 volt DC and AC, and it's got an auto manual mode. So the manual mode was quite useful when we were there out testing to wanted to sort of turn the radar on the spot, so we put on a manual, and then on auto would rely on the seismic sensor. We just had to make sure. I remember vaguely that I made a note to myself to leave the radar on the auto mode when you leave the site. Otherwise, all that hardware would be lost. And the last piece of the puzzle are the antennas. I mainly chose the frequency of the signal because of the commercially available parts. As you know, wide bandwidth. It also comes down to what parts are available. And because of the high gain needed, realized actually that band that we chose falls into a popular SATCOM communication link, KU band, which is the downlink of SATCOM communications. And the dish antennas have quite a high gain, linear polarization, and because of the offset feeding mechanism, they have a nice sort of symmetrical radiation pattern within the 3D beam for the antennas. I did some testing on the feed itself, because obviously these feeds are designed for communications that have one frequency band on one feed and the other frequency band on another feed. For radar, we're using the same frequency band, so just want to make sure if you feed it in one port, what happens on the other port, doesn't it terminate it or not. So some testing was done in chamber with different scenarios, and those results are all validated. So once you got all those pieces together, that's when the fun starts. So we did various measurements outdoor. Obviously, loop tests were done in lab, but that doesn't beat the measurements outside. So on the right, you can see this is one measurement that we did looking at a target just sort of 10 meters away. In fact, the range profile is about that picture there, and that peak there is actually my greenhouse, about sort of 15 meters away, with various targets that gets reflected back from surrounding of that target. We then took that radar and put it right outside our house, pointed at the road. We managed to scare some drivers driving around, thinking that's a speed radar looking at that. But that was quite interesting because then we could try and look at some moving target and see how the radar behaves when there's a moving target in front. And I think I believe that car is yours, that black car right in front. So that was that sort of helped with some stationary targets in front of the antenna. But we were lucky that while we were measuring some data, there were some cars moving around. I remember we matched the video with the range profile. You can see those movements tallying up together, which is really good. So we got a combination of trucks going around, some cars. We even got a person walking around, which is quite nice to see on the range profile. Yeah, so that's probably with that minute. There should be a person walking around soon.
This is just the raw range profile, not MTI profile.
No, this is just a raw range profile stitched together or streamed together over it. So there's a person. It should pops up. There you go. So that's on the range profile, which is quite interesting to see. Okay, so once that was all good, it was time to get deployed in Guatemala and try and image some volcanoes. So the volcano that we looked at is called Santiago, towards sort of the southern part of Guatemala. And there's this cool sort of website that you can go onto and get some real updates about when it is erupting and how many eruptions you get per day. So it was good to sort of prep yourself beforehand. Guatemala's climate, it's not normally, it's not defined by northern hemisphere seasons, but it's defined by dry and rainy season. So the dry season is about sort of from November to April. So that's a period where you really want to deploy your radar and get some data. After that, it starts raining. It just sort of becomes practical. We had a few locations to place the radar. Before we sort of embarked on the trip, we were under the impression that we could put the radar, so it's about 3 kilometers away. Looking up, that will create if you're looking up into the volcano, obviously you can get a sort of slant angle and you can have a wider beam width. But because of the various reasons and not having access to those sites, we ended up at a place that was about 6.5 kilometers away. This was extremely hard to get to. Not to mention that we weren't sure whether the radar would cope with that sort of long range. But nevertheless, that was where the radar was deployed.
What did that take your measurement cell? You said it was 200 by 200.
Yeah.
Initially, would that change? Did it change the?
So that 200 by 200 is when it's at that location. Yeah. Obviously, if it was closer and you look up, then it's not a symmetrical footprint anymore. It's more a triangular. So again, just to recap what PDCs look like and what we were looking at. The picture on the left is actually the one I took myself. So you can see that that's PDC coming along, and once it sort of enters the crater, it's got this behavior where it can take different paths. So again, that's another decision that we had to make. Where do you put the radar? Do you put it in front of the volcano, side, back, and depending where the PDCs flow, you might miss and you might capture it. So this is the one that sort of comes in, rolls down the side, and it sort of comes down the volcano and deposits itself towards the bottom of the volcano. The middle one is that shows different paths they can take, and then the right one, I'm not glad that's not me taking that picture. That's the extreme case or what could happen if it all sort of goes shebang. That's our radar stations. So again, talking about that sort of not being able to see the volcano at part of during the day. Believe me, there's a volcano behind that cloud in front of the radar. And yeah, so the radar sort of has a line of sight to the volcano. We, by the end of the trip, managed to tidy things up, seal everything, make sure everything works, and sort of check power and DC and RF. So you can see our solar panel. The one problem with the solar panel is actually they get covered with dust. So even when we were sort of there, they will also get covered with dust, and you have to sort of keep cleaning them. And yeah, so that's the station itself. So once you got the radars installed, your next challenge is how do you make sure you're looking at the same spot about 6.5 kilometers away. So that is obviously we got pencil beam width. Yeah, you can't just you can't have transparency in parallel to make sure and hope that you get returns. No, they have to sort of overlap. So one way was to have a continuous wave source placed at far from the antenna, and you peak the antennas. So we put together a box. This had 2 modes. You can either have it as an active target, so just relaying what is received, or change it to a continuous wave source. We use a continuous wave source to fly away, transmit, go on one of the antennas, use a power meter, do a course alignment. Once it peaks, lock it in and leave them there, and then go to the next one. So we use that in tandem with geometry that you get from Google Earth. So you get access to elevation, height, and you can put pinpoints that gives you the locations like a notch, magnitude and shoot. And yeah, so once you carefully sort of study those, then you can align the antennas nicely. On the left, you can just about see the drone at about 300 meters. Anything more than that, you can say goodbye to the drone. In fact, it nearly happened. We sort of lost the drone at one point, and we had to go and retrieve it. But because of the payload and the wind and thing, it becomes unstable if you try to fly more than that. So I said about just verifying that the drone is in the beam. So we use the Google Earth, and we come up with a waypoint that can be programmed onto the drone. So this is actually what the beam of the antenna is looking at, electrical beam of the antenna on the volcano. So once we put those, we wanted to verify actually the antenna is looking at the spot. So we put those points onto the drone, flew the drone from the radar to the volcano, hover, and then back. So on the left, you can see so this is the MPI processing that my colleague Jim has put together from the offline data that we got. So on the left, it's very sort of self-explanatory. You can see the drone flying away, staying for a bit within the beam of antenna, and then flying back. So this is all sort of good verification, and the antennas are all well aligned. So there it is. On the right is a range profile of the volcano. It's about 6.5 kilometers away. We were so glad that it actually turned out to be a big target. Very nice to see. Very relieved once we saw that signal. And yeah, so from the data that we managed to retrieve, there's still some analysis to be done, but on the left it shows the processing again that my colleagues done on this, trying to separate out the up and down chirps and figuring out where they finish, so they can be processed correctly to produce a nice FFT range. Yeah, so on the right, it's a simple range profile that you can get. On the left, that process is automated. And because on the first iteration of the system, we didn't have that drover signal. It's a signal that indicates where the up and down chirps are happening. This process is a bit slower, but with the upgraded system, we now have that signal, and this will help speed up this processing. It will tell you exactly where the chirps are finishing, so your algorithm can tie that up together. And then, yes, so we started thinking that if we get 12 PDCs, this project will be successful. We ended up with about 469 data sets and about 100 PDCs. On the bottom, you can see pictures of Pyroclastic flows, and tying those data sets with the seismic activities that we recorded. It shows a really good alignment between those two. Obviously, there are false alarms, but you just disregard those data sets. So those the pictures on the left show early initial sort of analysis of PDC that's still happening, but that's it. This is the flow that the radar has picked up. You can actually just about look at what the velocity of the flow is. So that gradient there shows about 10 meters per second, which actually tallies up with some of the linearity of similar PDCs and their velocity. So in summary, we managed to put together an XKU band radar, Guatemala successfully picked up PDC flows. Ever since the first trial, we've had a second trial where the system has seen some updates. So this is new acquisition software, so it's based now on Linux rather than Windows. The radar receiver is now isolated in a separate box, just to keep it nice and sort of shielded. And we are using also a wider beam antennas. So these antennas actually double the beam width, so it should hopefully help us capture more of the PDC on the volcano. So this project has been on a large scale, and it wouldn't happen without the help of friends and colleagues. So special thanks to my team, colleagues, local authorities who were tremendous help, and also Spectrum Instruments who gave us a lot of support on their part. Thank you for listening. That's the presentation. Yeah, any questions?
I think we're going more and then stop recording. Yeah.